Hello all, welcome to Unit 7. Today we'll look into waves, interference, and diffraction. We'll consider three different waves. First is the sound wave and water wave and light waves. They both have very similar physical properties, as you will see. Um, this one I've shown here uh, diffraction pattern for green light, and so we'll focus more into the light interference and light diffraction because these two experiments established light as a wave. uh, by now you know that particles or waves, they both carry energy with them. We did particles last semester, physical bodies like rocks, thrown off the cliff or football thrown at some angle. And also we did the electric and the energy carried by electric waves and magnetic waves. Um, so some of these mm, bodies, they are only particle like, and some of these um, the physical parameters like waves, sound wave, water waves, they act like waves and both particles. This is the something interesting phenomena shown by light, because light behaves both as particles. It has tiny little photons, that travel through space-time, and at the same time, light also behaves like waves. And there are two types of waves: the longitudinal waves and the transverse wave. If the direction of the wave is in the same as the wave motion, if it oscillates in the same directions, like the sound waves, is the oscillation of air, air particles, the compression and rarefaction of the air molecules, which we can represent as the wave. It happens in the same direction. These sound waves are longitudinal waves. The water waves that we see in the lake, pond, or oceans, these are transverse wave, and so are the light waves, meaning their direction of the motion, as you can see here, is perpendicular to mm, uh, their oscillating direction. Here the wave direction is to the right, but they are oscillating vertically up and down. And we can, also characterize these waves are mechanical, electromagnetic, and gravitational waves. The sound waves, water waves are mechanical waves. The oscillation of all the spectrum, electromagnetic spectrum from radio to visible to gamma ray, all these constitutes of electromagnetic waves. And there is third one, the gravitational wave. The gravitational waves are created when two very massive objects like neutron stars or black holes come to a violent end. They create these um, ripples in fabric of space-time, and these ripples travel outward as gravitational waves. Uh, uh, Today we'll explore, wave phenomenon of light, more focus on that one, and we'll look into what interference and diffraction is. Waves, in general, we can label waves, by looking to their, geometrical shape. And this is true for all types of wave. For wave, we have amplitude, the height from a horizontal reference line here, the central horizontal line, the height to the crest here will be amplitude, and these velocity these wave travel at some speed, so they have that velocity v and given is to the right, and we'll measure the length from one point of the wave to the other one, called the wavelength, uh, and denoted by lambda. We can measure this wavelength from crest to crest, or from trough to trough, or from any other cycle, as long as it's one complete cycle. Okay, it is if it starts here, then it would end at one cycle at that point, and that's the uh, that's the wavelength. And the mountains, the peak side are called crest, and the valleys are the trough. And if we know the frequency of these waves, the cycles per second is called the frequency, or here you can see clearly this the time frame here I've chosen as 1 second. So how many times it makes one complete cycle in 1 second is called the frequency. So here there is 3 cycles in 1 second, hence the frequency of this wave is 3 hertz. If you know the frequency of this wave f, and you know the wavelength of this wave lambda, you can calculate the velocity of this wave v as lambda times f. And the time period is time taken by the wave to make one complete cycle. So here this is one, the time period of this wave, and frequency and time period are related by inverse relation. The time period is 1 over f, or frequency is 1 over t. And now let's look at the interference. Two waves, uh, Young, Thomas Young, one of the physicists long time ago, 1801, he did this double slit experiment to prove that light behaves like waves. It was the first experimental proof that light behaves as wave. Here are first we need to look at two wave properties. First, wave A and wave B. Here, as you can see, if wave A and wave B are in this pattern, they are meeting here in phase. Their trough and trough are aligned, and crest are aligned at the same time. And in this case, it forms a constructive interference. The troughs align, and the amplitude of the trough increases, so does the amplitude of the crest. So now A plus B in this case forms a constructive interference, and we can have second case where they are out of phase. Here the crest and the trough cancel each other, and so does the trough and the crest, and so this canceling results to a flat line, or the if these are light waves, and if two light waves have this type of destructive interference, they cancel the light, they form a dark band in the screen. And so this is an example here. This is not shown in forms of wave, but a general idea that light also travels as a plane waves. So, and as light enters through the two slits here, the light bends. This is the diffraction property of the light. When light, the light or any waves, I should just say waves because this works for both light waves, sounds, or even water waves. And so the bending of the waves as they enter any obstacle is called the diffraction. And this as the light diffracts from this pinhole, these little wavelets travel in all directions. So these little circles here, as you see, they increase in their diameter, and so one half circle expands to downward, and these downward, and this at the bottom, the other half circles expands upward, and these two circles kind of intersect. Okay, and that intersection point can be both the constructive interference or the destructive interference. And if they meet constructively, we would see a dark, bright band here, and maybe some distance higher, a dark band, and the bright and dark. So we see these fringes of dark and bright, bands of light. And here is more, geometrical explanation of double slit experiment. Uh, Similar setup. Light enters through two slits, and as they diffract, uh, this consider this as the upper slit and the bottom slit. So this is the upper slit, bottom slit, and so from here we're taking one wave of light at a time. The vertical line here is would be that vertical uh, to right where I'm pointing here at the center between the two slits. For one example, we're taking the wave that are both directed at theta degrees from the horizontal. So something like this wave here. So we're only taking two waves, and so one is ahead, so this one is leading the bottom one because the bottom one has to travel extra length, this distance here, which is d sine theta. If this is theta, that's your slit difference, from center of top slit to bottom slit, slit distance here. And so this length is d sine theta, also called the path difference. And on the top here, you can imagine, go back here and see if both of these waves, meet constructively at that point here, we're going to see a constructive interference or a bright fringe here. And if they are out of phase here, at that point we see a dark band, or a destructive interference. And the condition is that if this path difference here is integer multiple of the wavelength, that's the integer is m multiple lambda is the wavelength. If this path difference, which is d sine theta, this path difference is equal to m integer multiple of lambda, 0, or 0 is the case for the theta equals to 0. So the horizontal band, so this one here where you see a central maximum case, and m equals to 1 means d sine theta equals to lambda, d sine theta is 2 lambda, 3 lambda, 4 lambda, and so on. If this condition satisfied, we would see a bright fringe because of the constructive interference. And if this path difference is integer plus half, 1/2, 3/2, 5/2 lambda, then we would see a destructive interference, or the minima, first order minimum and second order minimum. At the same time, for m equals to 1, 2, and 3, we would see first order maximum, second order maximum, and so on. And this is again, in order to see this type of interference clearly, we would need to use monochromatic light source, the light source with only one wavelength, so single color. Uh, the regular light has multiple colors with multiple wavelength, and these would interfere with each other and smearing out the whole pattern. And so it works better for monochromatic light, single wavelength, just one wavelength. And so here in this relation, we can see d sine theta is m lambda, and by increasing d or angle theta, or lambda, we can vary, other physical parameters. Like if you increase d, your lambda would vary. Or if we use light with different lambda, or a source with different lambda, we can increase the wavelength of the light, increasing here, that theta would vary. Meaning if theta varies, then the diffraction pattern would be observed at different distance in the screen, in the side. So you see, you can um, answer some of the, these quick multiple choice questions. What happens, or how to increase theta, given d constant, m constant. So how do you vary lambda in order to increase the theta? These type of questions. And we have such questions in the lab today. And diffraction through a single slit, similar explanation as the previous interference pattern. Here we'll look into minima only. You can refer to the book to see the maximas here, because other maximas are so small. Here the central bright fringe is very prominent in single slit diffraction, where m is equal to 0. Similar principle applies again. Diffraction is the bending of the waves, bind obstacles in these shadow regions here. This is basically what diffraction is. And if you decrease the slit width here, that diffraction is more prominent. And this is these here, we can, these arrows here, we can consider multiple arrows, like in this example. And so this one wave leaving at that, in the top point, the bottom point, we can compare these two waves. And similar explanation as before. You can consider, how the top wave and the bottom wave interferes as they hit the screen at the end. Here you can see little details here. Some of the waves are directed this way, that, and this is at m equals to 0, or the horizontal case, and others are more angled toward upward. And uh, same as here, how the two waves, interfere differently when they hit the screen, meaning constructive or destructive. In this case, d sine theta is m lambda. Here d is the slit width, while in the previous case that d was the difference in height, or the length of uh, um, length between the two slits. Here it's the width of the slit. And that d sine theta is m lambda, where again m is integer. Downward you can take -1, and upward to the right you can take the +1. And when d sine theta is m lambda is satisfied for m equals to 1 to 3, we get the minima here. So, the lambda by d is, when m equals to 1, sine theta is lambda by d. And when n equals to 2, it's 2 lambda by d and 3 lambda by d, and so on. And even here, when you can change the theta, when you change the theta, lambda can increase. Or if you have control over the light with different wavelengths, we can vary lambda, and by that it should change the sine theta if you keep d constant. Okay. And so you'll have to analyze these type of equation to answer some of the lab questions today. And so that's the basic of the waves, wave interference and diffraction. We'll apply this in all three types of waves: sound waves, water waves, and light waves in today's lab. So let's look at the simulations. This is the manual for today's lab. First, we'll look into waves in general, and we'll move on to the interference and diffraction um, later. So here, develop your understanding of the waves. Uh, it, It's a simple, nice simulation site here. Click on the waves link. That should directly take you to the simulation site. Um, you know, play with all these buttons and see what they do. If you want a continuous wave, pick that one. If you just want one single wave, you click the bottom one. For example, I'm starting with the water wave. So this creates a water wave. This creates a sound wave. To turn it on, press the green button, and this one creates a light wave. You can choose your color. Choosing different color means, remember, you're choosing different wavelengths. Uh, and red has the largest wavelength compared to the blue. As you increase the energy, you're decreasing the wavelength. Uh, so I'm picking red, or you can pick somewhere in the middle, green ones. So with light, you can change the frequency of the source. Here you don't have exact frequency, but you'll see the variation in the waves as you maximize the frequency or minimize the frequency. And for water, you can do the same. You can have the maximum frequency uh, and the minimum. So these are waves here. The dark means the trough, and the bright means the crest. So dark as the valleys. So this is the bottom of the wave, and the bright ones are the top of the wave. Let's see if we can see this sideways. So the water drops and it creates these waves. So now it's clear what the trough is and what the crest is here. You can slow it down, uh, normal speed, top view. I like the top view. If you just want, there are cases you may want to try just one wave, single wave. So let me just draw one drop of water, and you see the wave like that, and it's more prominent in side views here. So you see that one wave travels instead of continuous wave. Okay, so let's pick continuous wave top, and here in what are the questions. Uh, so wavelength in centimeter, longest wave possible, wavelengths of shortest wave, height, period. So you'll have to measure all these, geometrical properties of the wave based on here. How do you do that? Uh, so first, play with it and see when, it creates this longest pattern. uh, Longest band of bright and white lines here, which represents the troughs and crest. And so frequency, if I decrease the frequency, or for the minimum frequency, so for minimum frequency, see, I'm getting the largest gap, right? You can also see from here. So you see the longest wavelength is created for minimum frequency, and so on. So top view, how do I measure the wavelength? So yeah, I will, so at that instant I'm pausing it here. So this is my crest, this is my trough. I'm gonna take my um, ruler here, and I try to pick the center of the dark band here, which is the trough, and to the center of the crest, and that, or from the I think I need to, if I increase little bit here, because that is my wavelength. I was gonna measure half and multiply by 2, but I guess I can simply increase, consider that as my central, sorry, as my crest, as my peak, and measure that distance. That should give me the maximum wavelength. Okay, and yeah, or you can also that should do it. You can also measure the dark bands here. Uh, can you measure this thing here? Yeah, you can also pause it at that point, especially if let me reduce the frequency. And right there, so between here and here, maybe that's the peak here and that's the peak here. You see in this fashion here. And so in the question, you'll have to tell how can you, have the longest uh, wavelength, shortest wavelength, and and so on, the period, and so on. Also, here when you get to speed, calculate the speed of this wave, and if you know the frequency and the wavelength, that's the wavelength and the frequency, that will give you the uh, uh, use the formula here. Can we have the formula here? Use this formula, this labels here, this geometry here. If you have lambda and frequency of that, you can calculate the speed, velocity of the traveling wave. And you know what time period is now. You can also use this feature here to, I like it this way, move it up. If you want to time it, say that, you can time it, time it takes for the wave to make one complete cycle up here and stop it. So you'll have to put that in somewhere, anywhere here. And as soon as the crest reaches your let me put it horizontal so that I minimize the error. When you put your here's the crest, and you can time that crest movement when it gets to the other side. Okay, and to get that one time period. Uh, Also, to move on, so that's the summarize your understanding of waves. Uh, so, based on what you have done here, calculation of your wavelengths, heights, and how to change the wavelength, how to get the longest wavelength, shortest wavelength. Same thing for the period and speed. Once you do that, simply summarize your understanding, behavior by comparing these different waves. Use vocabulary words like frequency, amplitude, wave speed, and so on. Also, the amplitude is the wave, the height of the waves. So for that, you may have to come here, and if you show a graph here, you can see these waves in the form of graph. Uh, I have the maximum frequency for maximum amplitude and maximum frequency here. Um, for this wave, I can calculate the amplitude of it, like this one here. Set your scale and measure the amplitude of it and see in what case you compare how frequency changes the amplitude of your uh, waves. And so when do we look at, so next, um, understanding of the sound wave and the light waves. So after that, you can switch your experiment to sound and the light. Very similar. You'll see very similar graph, all the way. This is here light source. You can pick what color light you want, red to blue, and compare the representation of water, sound, and light wave. Describe the similarities and differences in the images from the simulation to support your ideas. Okay, so uh, take a screenshot of all of these water waves, sound waves, and light waves, and what are the similarities and main differences, right, between water, sound, and light. Where do you see difference? The label are very similar. The formulas are same. The speed of wave is same. The amplitude, the crest and trough, the interference wave is same. But we haven't looked at interference yet. Only so you'll have just to write, how they are similar or how they are different. For example, for light, here you can see I can pick the frequency based off of the color, right? And I know these frequency values for different colors. However, for sound, there's just some random values of frequency, some maximum value and minimum value. But you can explain how the wave pattern changes by increasing the frequency versus decreasing the frequency. So that all goes in here. And the next one is the interference. Open your interference screen. And now you have two sources, because to interfere you need we are using the two sources of water drops, are sound source, the speakers here, or the light source. Okay, same thing, we can use first water. Turn on the water, drips like that, and as you see, as the water drops falls on the pond, then it creates these two waves. These waves, this one and the bottom one, as they travel outward, they interfere with each other. And that interference here, you can see the bright ones are the crest, that's the constructive one, and the troughs are here are the destructive ones. How do you change the interference pattern? You can play with the frequency. What happens, you increase the frequency, or what happens when you decrease the frequency, or what happens when you increase the frequency. Okay, here answer these questions. And I here the three examples are given, ABC, which you can create for your own. One is for the maximum frequency versus low amplitude, or the I'm gonna give the average amplitude or the average frequency versus high amplitude. Yeah, I need to give some. So wait some time before you start see the clear picture, because it needs time to evolve. And so that's for this low frequency, high frequency, that. And you should see some significant difference when you change the separation, because this is the slit width, sorry, slit difference. We are using two different slits. So that's for the minimum at 1 centimeter, You see how the fringes, how far apart they are, the separation, how the bright fringe is more visible. The constructive interference is more compared to destructive. I'm keeping these at the farthest separation, and how I see multiple constructive and destructive interference pattern. Okay, and there's one more thing you are asked to do here is you can also see these in the form of waves. So let me make a nice wave pattern here at lower separation distance, and uh, here I can see the I wish there's a way to increase that oscilloscope. It's showing me the graphs here. I can lower the amplitude a little bit so it's within the frame here. Okay, so that, let me pause it. The good way is you can slow down the simulation, or just pause it for a second. And now I'm going to measure the the wave pattern of the wave here, the water wave here, for when it's at the uh, crest and the bottom. So here, you know when I play it, I should see two graphs here, two oscillating waves, showing water levels. As you can see, they are out of phase because we're measuring at the crest, and when you're measuring at the crest, at the same instant you're measuring the trough. So when the white one is at the trough, the black one is at the crest, and vice versa. So these are exactly out of phase. If I were to pause it and if I want to measure both at the crest, these will overlap. Well, not exactly, because here, let me. Okay, so now you see they are like almost overlapping with each other. We can do the same thing for the light waves. Pick any green band here and see if it works out. Maybe it will be slightly different. So now they are out of phase. I can pause it and rearrange it, because we choose different frequency light. It may not be same as the sound waves, and the number of interference pattern here will also differ based on the frequency of the light. So now they are in phase, uh, and so for the um, lab report purpose, please take the screenshot, hold the screen here. Again, um, um, I prefer nice screenshots and not the random picture that you take. When you take picture of it, you see there's glare in the screen and it's very hard to read the diagram. When with a screenshot, it minimizes all those glares and you'll have the best shot. Here for the the interference pattern, you can also see the graph, or I prefer the screen here. So this screen, is the point where these two interfering light waves meet, and so every these green bands mean there is a constructive interference happening, while this type of pattern here, when they meet at the end, there is a destructive interference happening, and you see these dark bands here. Also measure here and see what happens. So you see here the amplitude has gone almost to zero, right? When amplitude is zero, it's a destructive interference, and versus here, compare these two, you'd see. Uh, okay, I think I have explained pretty much everything that you need to complete the lab. You can change the color, or you can just refer to this diagram, or you can recreate this image by choosing the blue light here. May not need this thing here. You can recreate your own diagram. You'll see the constructive and destructive blue fringes here, and explain, where the points of constructive and destructive interference are in the image on the right hand side. Create your similar pattern, explain how you made the waves, and use the detectors, and use your entire screen for evidence. And the last part is the diffraction part, and it's a short section. However, this is quite interesting. For this one, go to the diffraction link, and this is your light source here. Once you turn on the light, you can pick your color, or you can pick your wavelength. See what happens when you increase the wavelength and decrease the, sorry, this is your increasing the wavelength. As you decrease the wavelength, see what happens to your fringes. Also, what happens to your central maxima, the width of the central maxima. So for for the lowest wavelength, when you decrease the wavelength versus when you increase the wavelength, see what happens to your central maximum. Okay, this is the main understanding point here. So for increasing wavelength, write down how this central maxima changes based on the equation d sine theta is equal to m lambda. Okay, and this is for your aperture. Here we are picking as a circular aperture. For that circular aperture, I can decrease the aperture diameter and see how my central maxima increased, versus if I increased the aperture, how the interference pattern, diffraction pattern changes. This is for the circular case. Eccentricity is 0. I can increase the eccentricity, meaning I can increase the flatness of that circle and see how the pattern changes. Right. I can also have a square aperture. I can have both, and now it's like a two slits here, and you see this type of pattern. I can have multiple squares, or even a shape of a person, and so on. So you see, in short, your screen, what you see in the screen, is reflected by the aperture shape and size. Okay, that's one. And the other questions here, your wave interference, with both the slit and diffraction. Use your ideas from wave interference about what happens to the wave passing through slits, through round hole. Make a pattern, explain what you think is happening, including images to support. Compare pattern of various slit size to pattern of varying hole size, including images to support. Here you can go to this the simulation side with different options. So I can pick here at the bottom. You can choose between slits and the diffraction simulation page here. We just did the diffraction one, and let's look at the slit. This is a single slit here, where I can vary the distance from the source to the slit. Turn on the light. Let me choose my source here, the light generator. You can also pick water. So you could repeat some previous examples using this simulation as well. Here the single slit, we did the double slit earlier. Same thing for the you can do for the sound, but the lab question only asks for try for the light waves. Let me verify that. Yes, for the light, and so I'm picking the light source here, and see how the interference band changes here at the end. Uh, I like to see it as a screen here. So this is a diffraction in a single through a single slit. So as I expected, I would get a central maxima with highest intensity, and the minima are quite far up here. So it's hard to see first minima and the second minima. Uh, and so how can I change that? um, try your try increasing the uh, slit width here and see how the pattern changes versus for a small slit width. This is in nanometer, so that's 500 nanometers, so width is in the nanometer scale. I can so that's that. Increase a little bit of slit width here. I can also check for the intensity graph here, uh, and examine this intensity line as for different what happens when you change the wavelength of the light, what happens to the intensity. And so for red light which has a longer wavelength, compare this intensity to the blue light or the violet which has the shortest wavelength, and compare this intensity. Okay, what else? Uh, and again, use all these uh, all for each question. Wherever it says here most of the time. Include images for the support, because every time you do different set of experiment for to support your reasoning, please include this screenshot here. If this here intensity is hidden, so you can zoom in a little bit and zoom out a little bit to show the complete intensity pattern, and compare to the green. Okay. It's always good to look at three different range here, for the largest wavelength to the shortest wavelength. So yes, again, explain how the aperture geometry relates to the diffraction pattern and predict how changing the wavelength or aperture size affects the diffraction pattern. So after completing all these experiments, in this one here, you have to write down how changing these different aperture shape and size affects the diffraction pattern, and maybe and also how changing the wavelength changes your diffraction pattern. So aperture shape, size, wavelength. So basically you have to write down what factors does the diffraction pattern depend on. Physical factors, shape, size, wavelength of the light used, and so on. And same thing for the single slit experiment. What does this the diffraction pattern here you see depends on, and these variable. right? I mean, yes, it does depend on frequency, wavelength, and the distance, and how far apart they are. You see, the intensity decreases, right, when it's in. Yeah, I mean that you can measure it. So the intensity varies here when you decrease this length versus this length here. The okay, and how does it depend? Okay, that's more important. I know it depends on the this length here, slit width, and the frequency and the wavelength, but go back to your equations and see how one changing one parameter affects the other parameter. Okay, and finally summarize your findings. Your understanding of the waves, uh, and here it says demonstrate if you meet the learning goal, and those learning goals are within this section here. Predict how changing the wavelength or aperture size affects the diffraction pattern. So, uh, how do you learn this? Explain it here with the support of this diagram here. So, change that. Let me pause it here. You can put this thing in multiple regions like this. This is dark, bright, and call that the gray, the intermediate color zone here, versus the dark zone, and see how that varies. So you see they're not exactly out of phase or in phase. They are off by, maybe 45 degrees. Not, not out of phase by 90, opposite. So you get my point. So, sometimes these waves not necessarily have constructive interference or destructive interference. Not like there's no either black and white. So there's a gray zone here where they are partially constructive or partially destructive. And that's what creates these uh, uh, the gray zones here, not completely blue band and not completely the dark bands. Same thing with the light. Let me pause it here, and even in this type of zone here, the between dark, if I put it dark, and the gray zone here, uh, slow down a little bit. So you see they're just off by a few degrees, but not completely constructive or completely destructive, and that's what creates these gray area. Okay, with that I'll stop here and take questions.